Hey Dave, hi. Looking forward to this. I hope you can hear me. A test, a test. If someone's out there, you can't see me yet because I do have this startup screen here that I don't know. I like to use it. But you should already be able to hear me at least. Not sharing anything yet though, except for my decent voice. I want to say except for my beautiful voice, but that would have been a little bit exaggerated. But yeah, let's start. We can hear. Hey Matthew, hi Tunde Tundle. Uh, ah, Perfect. You can hear me. Let's go. So, wait. Let me. I have been a streamer a couple years back, right? I have like a stream deck that I set up today, and I will be testing it. Sorry if you get sick if I jump around there. Hey Rednet, hey Omar, hey Sushil, hey Musinj. Difficult name for me. I'm good. I'm good. Thanks for asking. How are you? Yeah. So I today I set up my stream deck again. So I'll be playing around with this a little bit. There's not much. That's it. I do have those buttons that I play around with. So if I mess up the screen today a little bit, that's totally on the stream deck, not on me. I set it up and I'm the one using it, but it's definitely the tech that does that creates the problems. Yeah, finally catching me live. I really helped you. You are very welcome and glad to have you here. uh, yeah, so I'm basically online every Tuesday now, right? So this is the fourth time, a full month. Yes, I kept my promise for a whole month. I said I will be online like the upcoming weeks, and it has been for a month, not 4 months, 4 weeks. So it's been 1 month. Hey, that's something, right? Yeah, those are also quite fun. And today, right? As always, agenda is a little bit small talk here in the beginning, a little bit getting into it. Love my videos. Thank you. I have never watched my videos. I gotta admit, 98% probably of those videos that are up there. I I did two things. I always did all the programming in preparation, like on my own to test if everything is going to work out. And then I just filmed myself doing it again. Like, no cutting in there. It's literally 100% what I was doing, like in the programming, like one to one. It's literally like none of my videos are cut. Right? Very rarely, maybe I cut out like a very bad thing or so, but no, it's all live. It's all just me directly doing the thing and then uploading the video. I couldn't stand myself watching it. Like I was watching the last live stream just to check out a couple of my settings an hour ago or so for testing, and I was like, oh God, my voice is so annoying. I always thought I have like a rather deep and okayish voice, but no, I don't like my voice. uh, hey, from the Philippines, that's a new one. I think I haven't read Philippines yet. Yeah, so the man, the myth, the legend there. I don't like my own voice, at least in the recording. Right? So maybe it's the microphone setting. Maybe I'll just have a Stream Deck button that makes my voice go deeper. Or so yeah, so all my videos pretty much uncut. Right? Also the live streams, you will see me make errors, especially today, because I did prepare. I understand what I'm doing, but there's a lot of things that I will also be exploring, explaining along the way, and having fun along the way. Nevertheless, right? Nevertheless, there might be one or two smaller issues today that I will get into, and we're gonna have fun. We're gonna learn from it. Um, but it is a rather intriguing topic, and I do hope I can finish this in 2 hours because there's a lot in there, right? The live stream's always 2 hours, so yeah, probably I can finish a little bit, hopefully all of the parts, right? And it's a very very interesting, very big topic, but as long as I still run on my like 30-day version of Factory I want to use it. So today is the last time for now that I use Factory IO, and I wanted to do something with it. So maybe I'll have to get a license for the next time, or I will get into more tech topics next time, because Factory IO itself isn't like, it's for learning, it's for beginners, but it's not the most like tech thing, right? So yeah, Hi from India. Yay. Instrutronic. India, I know I have a lot of viewers from there. Like I can see my, what's it called? My analytics and a lot of viewers from India. Let me actually check. I haven't checked those in so long. I am the worst streamer slash YouTuber slash content creator ever. So my viewers, most viewers are from, you can make a guess. Actually, India wins. Wait, can I show this information? I think I can. Wait, let me. I do have the list there. King of Automation. Nah, there's way better. There's way more. Uh, like there's way better people than me in automation. I just do some of the online stuff there. So let's see. And then I'm gonna start. Me big. Yeah, me big is a good scene for this. Oh damn, that's I have to flip myself. That doesn't matter. But you see, India place 1. This is all in German, but Germany second place. United States. I didn't know that Siemens was this big in United States, but United States on the third. Poland, United Kingdom, Turkey, Sweden. Yeah, but Germany wins when it comes not to the clicks, but on the amount of hours watched. Yay, at least something. There's so many German tutorials. Why are Germans watching me here? Strange, very strange, because all of my tutorials are in English. Perfect. Alrighty, that's good there. So let's get into the content. Oh, but did my camera freeze? No, wait. I do see my stream on the right side, and my hair today looks like blech. Usually I wear headphones, but I didn't feel like headphones today because there's no sound that I listen to anyway. I would say let's get into the topic. I hope so far your week is good. I haven't been doing much today. I've been just so lazy. It's crazy. So I was looking forward to this so I can do a little bit of stuff. There we go. Hi, Satish. I'm good. I'm good. Thanks for asking. So, wait, no, that's not what I want to plan. Yeah, Nitin. I gotta talk German. No, I'm not gonna switch to German. No. If you want to hear me speak German, right? I do German. I do German streams over on Twitch, right? On Twitch, I am online and speak German quite a bit every. I don't know what was it, Wednesday, Sunday. I do Twitch stream as well, but that's gaming and that's in German. That's like a hobby. This is also a hobby here, but the other thing is more of a hobby. Please continue teaching ProDiag. Hey Dublin, I read your comment earlier on, and as I said, I have added the ProDiag on the list somewhere here. I've added this under languages, right? But you see, the list is so long. Oh, the list is so long there. Can I help with your PLC program, please? I mean, if you have questions, you can put them in the chat, and we can all work on it together. So we'll see. But maybe. Yeah, first thing that I always do, which is completely. Like, you don't have to click on this or something, but it's like I created it, so, and that's the biggest advantage I can get here, is to promote my Udemy training there. Let me pin this. One thing that I found very interesting with the Udemy code here that I'm sharing right now. You don't have to use it. This is. I'm going to pin this just so I have the advantage of advertising it. If I have the platform, I can advertise my stuff. So if you want to learn from me, use the link. If not, perfectly fine. Now, what I found very interesting, I don't make the Udemy pricing, and I looked at it earlier on, and it was way more expected than I would set it. But it goes up and down. Like, the pricing in Udemy is crazy. Like, it's automatically generated. I don't understand it. Very strange. So it was like 3 times more expensive than what I would set it. Strange. But it goes up and down. It's literally strange. So save the link, and once you can afford it, once it's cheap, go and get it. Or don't. Perfectly fine. Can I make videos on Semantic Manager? Satish, I was always thinking I should. That's a very, very good point. And I do have this. Look at this. Other tools. And I'm going to put Semantic Manager on there, because that is definitely something I should actually be doing, which is also called nowadays. Right? Semantic Manager nowadays is also called TIA Classic. Right? TIA Classic. Now, Satish, an information, an interesting fact about this. TIA Portal. So let's start learning, right? TIA Portal. TIA Portal has in the background, right, something called Step 7. Right? Let me zoom in. Wait, I gotta change my screen. I hope this doesn't mess up the whole stream here. I hope it doesn't mess up the whole stream. We'll see. But I have to change my Windows settings in order for my what's it called? In order for my TIA portal to zoom in, which is so annoying. There we go. So let's see. So TIA portal has something in the background here, of course. Right? It uses licensing, and there's a software. If you if you go on the installed software in TIA portal, it will say actually Semantic Step 7. Right? So the base thing, the core of TIA portal is called Step 7. Right? Now, Step 7. Very, very quickly, Step 7 is actually a German, like, no one knows this, but it actually is a German abbreviation. Not even TIA programmers know it, but it's called Steuerung einfach programmieren. It's called easy controller programming. That's literally what Step 7 means. And that's what we have. Now, Step 7 is another word for programming PLCs from Siemens. Programming Siemens PLCs is called Step 7. And Step 7 in version, everything less than version 10, is done in Semantic Manager. And everything above and equal to version 10 is done in TIA portal. So Semantic Manager, right, is the core of it, is the same thing as TIA portal. TIA portal is just a new tool for it, and of course TIA portal is much bigger, but the core of it is the same thing. And there we go. Now we learned something. Interesting stuff. That is also why the first TIA portal version that came out was TIA version 10, right? Because everything below that is reserved for Semantic Manager. And Stuxnet, yes, that was back then with Semantic Manager. It wasn't developed in Semantic Manager, but it, of course, attacked Semantic Manager devices. Also, hello there. Hey, Lean, you got a job because of my video. Like they helped you. That's good. I'm happy to help. I hope you're doing a good job. If you're doing a good job, always say, yes, my videos helped. If you're doing a bad job, I mean, also do so. That's fine. But I'm not responsible for anything. That's what I'm saying. Arun, advanced level DCS project development. I probably wouldn't. I'm not an expert in DCS. More PLCs, but I'll put DCS systems in here. In other tools. But I'm not confident enough right now to make a Udemy training in it. Alrighty. Hey, Fellwipe. How are you doing? Okay. I would say we jump into it. So I've been going through this, and I actually, literally today, I can't show it, but literally today, I get sometimes I get emails from you guys, right? From like people watching my YouTube channel or that find me online or so. And today I actually got an email that asked me about this stuff here. Right? Hey, sir, Mr. Hegermol, Mr. Philip, can you please help me with my project that I have where I'm using PID controls? And I, most of the time, of course, read through the mails, but I can't answer all of them because there's quite a lot. But I was also like, hey, that is the topic that I wanted to touch today. Right? So what I want to do, hey, Niraf, after a long time, it's been a month. I'm back for a month now. But yes, I'm back. Motor telegrams. Ooh, motor telegrams is a nice thing, which I will put into there. Which is not motor telegrams, it would be more Profi Drive. But yeah, when will I upload next Udemy? As I can only do that much. Sorry. I'll try though. Yeah, PID, exactly. That's Gautam. That's 100%. That's the thing that I wanted to do. So I got this email and I was like, hey, that's the topic that I wanted to talk about today. And I will try to put many things in there because PID is an extremely important topic there, as Firas says there. And it can be complex, but I will try to make it like, I will show in the end, our program will be extremely simple. Like the PID itself with Siemens controllers is simple, I would say. It is implemented in an easy way. So I will show something called a technology object. But until there, like I want to develop our own PID controller. And I don't know how well that is going to work. I have not done this in 20 years almost, I would say. Not 20, maybe I'm not that old. Come on. Maybe 15 years. I haven't done that. SCL structured programming is on my list there. With, of course, the Siemens guy. I always work according to guidance. I try. Liebe from Gießen, Hessen. Real life projects. I will have to see. I don't share too much from the real life, I would say. I will see. Oh, Gautam. Oh, yes, Gautam. The problem with... So, before I get into PID, answering the last question now from Gautam, one problem that everyone has with Siemens does things in a special way. And for Siemens, if you look at a word, if you say the first byte of a word is for Siemens the high byte, right? For most other devices, it's the low byte. So in a lot of places, you have to swap the bytes when you are going down on the address level. It is really annoying. Never understood why Siemens does that. Right? But you have to do it in a lot of places. Manually, sometimes manually. Let's see, object-oriented programming, but that's a different topic. Don't forget to give me a yeah. No, here's the thing. If I can develop a nice PID algorithm, and I'm not gonna do PID, I will just do program a PI algorithm now. I'll just develop one, hopefully. Then you give me a thumbs up. An old IHK-Prüfung. Oh goodness, I have not done IHK-Prüfungen in a long time. Of course, I've been involved with quite a bit, but I'll put that here. IHK-Prüfung. Oh, that would be interesting. There's probably a lot of public questions. IHK, for everyone that doesn't know it, is the Industriehandelskammer, which is the German like agency that like observes all of the rules in industry and so on here in Germany. And there are probably a lot of public questions from their public that we could go into. Explain MRP. MRP is also interesting. I'll put that on. But then I can only put things on a list. I will now do like the... Oh, did I close my document? Damn it. I will now do the... Where did my folder go? There. Let's start with the PID though. I can't, like, we don't have infinite time, unfortunately. But I will also put MRP domain on the communication list there. Communication seems to be like a very interesting topic for a lot of people, I've realized. So that's very interesting to see, definitely. Okay, let's go. I'll put this on the second screen here. So what I have prepared is absolutely nothing. What our plan is for the day here. Okay, yeah, I share my knowledge. Of course, if I can share it, why not? Why wouldn't I? So here is the plan. We do have this tank system here. Now this tank system can be controlled with a fill valve. So I can turn on and off the fill valve here, and there is water or whatever liquid that is leaking into the system through a valve system. Right? And the nice thing about the software is it even has a fluid simulation going on. And what we need to do, and a very, very common task in industry, of course, and all around us. It's not just industry, it's everyday life. It's you driving a car, for example. Like a very common task is to keep something constant or to go to a set point value. If you are in your car, for example, right? If you're in your car, in Germany, we have roads, like most roads that I drive on are limited to 50 kilometers per hour. Like if you're in a city, if you're on a road, 50 kilometers an hour is usually the limitation. Of course, there's differences. We have the Autobahn, which is unlimited, which isn't unlimited, but that's a completely different story. It's unlimited for most cars. But usually it's like 50 kilometers per hour, and you want to go exactly that, right? So what you could be doing, of course, Cause effect analysis. Oh, that's interesting. Um, so what you could be doing, right, is you hopefully go with exactly 50 kilometers per hour, like a straight line permanently. That would be perfect. You probably will not. What will happen when you drive a car? And me too. I'm not that. I don't even have a car. I have to use a rental, uh, which usually they are quite nice cars, but they are very badly sustained. The maintenance on rental cars is very bad. The ones that I use, which is car sharing. Um, but yeah, so usually what you will experience is that the speed in your car, in the same way the fill level in this tank here, cannot be kept too constant. Right? If I, for example, want to go to 100, whatever that is, I think this is in centimeters, a meter fill level. Right? If I try to keep that fill level here manually, right? Let's say someone is taking, I don't know, 2.0 out of the glass, whatever that is, and I try to keep this constant. Right? There are many problems. Is DCS possible with 50 round? I don't know. I would have to see. I would have to check it out. So, right, I cannot keep this like very steadily, like the same on the road. You can try to go with 50 kilometers per hour constantly, but it's very hard to really achieve. You would need advanced technologies. Like your brain, of course, is a very good controller, so it can keep the speed quite decently, but not perfectly. Right? The same way me here for the tank. I can keep the fill level quite decently, but it would take me quite a long time to actually keep it steady at 100. Of course, I can find I could find like the perfect solution here, but as in your car, as in this tank, there are a lot of outside disturbances. Right? That is always the thing that breaks everything. If there would be nothing influencing the system, everything would be fine. But in your car, right, the road condition changes, the wind changes, your foot gets tired, right? Your car gets it's not a big impact, but your car gets lighter because you're burning fuel, right? So your car gets lighter. The motor heats up, changing the whole motor behavior. Right? You have so many disturbances, so many different factors that actually change how the car drives that you have to adjust. Like you with your foot, you are a very good system. Air resistance, yes, the air resistance is very important in cars, you're right. Other cars stopping you, like in front of you, right? You want to speed up, but you can't. So many. Going around the corner is different. Right? Topologies. Satish, I will put the network topologies on my network topologies. Topologies. Misspelled. Who cares? This is my document. I can misspell things. So you're driving, right? The same thing here. So here, one disturbance is, for example, me being at the discharge. So I can take more liquid out or less. Right? That is what happens in industry all the time. Of course, sometimes you need more stuff, sometimes you need less stuff. Things are not really consistent all the time. Another disturbance that we can see is the waves forming. The waves forming is a terrible thing. It happens. We have to consider it. Right? Glad to see me after a long time. I've been back for a month now. But yes, thank you. So the waves. Another thing that is also simulated, as far as I understand this, is that the higher the liquid level, right, the more it wants to get out, right? The pressure overall changes. Right? I think that's how the simulation is written. I don't know, but I think that's one thing. So if I try to keep the level constant, it's different keeping it constant at 1 meter, at the 100 mark, and at the 200 mark, right? Because the fluid itself behaves differently depending on the mass, which I might be incorrect. I don't know how the simulation was written, but I have the feeling that it changes. Temperature changes. Right? The fluid itself, whatever fluid it is, if it gets hot, it expands. You have to consider so many things when you have a system that you want to keep steady. And that is our topic now. Hey, Jean-Paul. I saw you subscribing or becoming a member early on. Thank you very much. A link for beginners who want to study PLC programming step by step to learn PLC programming. I mean, my channel, of course, the link, my Udemy training there, or the main link that I will also share. I think I share this every time, but one source that I really like to use from Siemens itself is a free resource, and I'm just giving you a link right now. It is called SCE Siemens. Siemens cooperates with education, and there are a lot of free resources. Yeah, there are many free resources in the link that I'm going to give you now. You just have to kind of click through. There we go. That depends on what you want to learn, right? If you want to learn, for example, TI Portal, there's TI Portal modules, everything free, right? This is completely free, what I'm sharing now. This is the official Siemens documentation there for many industrial topics. So there we go. From Congo. That's at least same time zone-ish. Newest features, I will get into the PID features, I hope, in a minute there, Tim. Sorry, you shouldn't see my analytics going on there. Okay, so yeah, there is a lot of complexity in this, and we will develop. And I hope I can hurry up now a little bit because I am now very slow. So what I want to do is I want to develop a controller here step by step, right? Where I can also have the set point here. I have a knob. This is my set point. This set point, right, is if it is at 0, if I turn it all the way to the left, the tank should be empty. If I turn it to the right, the tank should be completely full. If I turn it to the center, the tank should be half full. Right? So the set point should, like, obviously, this is an obvious thing, I would say. Right? All the rest I will not be using, but I will use the set point thing here. Right? Which is right now at 5.0, so the tank is 3 meters, so it should go up to 150. And there's many things we have to consider here, but 2 hours. So now we really start with our content here. Okay, therefore what I have already done, which I haven't done actually, I did in preparation, but I closed it again, is this. I will be using TI Portal, and of course I will simulate my PLC here. The set point is our input in this case, yes. Or one input. We have 2 inputs. I'll get to that in a moment. I will have to I want to communicate here with Factory I/O though, so if you have the same setup, you will have to have PLC Sim Advanced license, which is then we have to change TCP/IP single adapter. There is another way in Factory I/O, but that's what I want to use right now. And then I want to add an S7-1500 PLC. This S7-1500 PLC has to have specific settings. The first setting, it has to have a specific name, which is Factory I/O. And the second thing is it needs an advanced license here. And now I run the PLC, and once this PLC is up and running, it should automatically connect to here, and this should turn green any second now. If once it started, right, you still, on the top left, it's still booting up. Come on. I do hope this is necessary right now. If this doesn't boot up, that's very bad. Why doesn't it boot up? Come on, please. I don't want to restart my PC. It might be that I have to restart my PC for this bullshit, because PLC Sim can crash quite easily. It's not a solid software. I wouldn't use it. Of course I do use it, but it's not the best software, I would say, because it crashes quite frequently. So while it is still booting up and trying to connect, let's hope this will happen in a second here. I will already go into TI Portal. I did create a new project. I want to use an S7-1500. So very quick, any S7-1500 should be fine for my course right now. I will still take a 15, whatever that is, and this one called PLC, have it, not version 4.0. I do hate the new user management settings, so I will go back to version 3.0. Not necessary, but I hate the new user settings that we have to do in version 4.0. I haven't adapted to it yet. Has it started yet? Fuck! Sorry. Runtime CPU error. It has a timeout. This is so stupid. Okay, here I go. I hate sometimes that Siemens isn't very good with Windows. Right? All of this is Windows based, but it's very, very terribly written. Some of it. Right? The problem right now is, oh yeah, that might be it. Oh, no, that was me. I had to accept the license agreement there. I'll take it back. It's still, some of it is written very bad in Windows, because I am using Windows Home Edition, and Windows Home Edition does not have the perfect settings that they use for this simulation software, which is just Windows stuff, right? But it's not perfect. If I would use Windows Professional, different story. But I use Windows Home, of course, on this PC. There we go. So now I have a PLC. This is up and running, and this should have auto-connected to factory I/O, hopefully. Yeah, it did. Green. There we go. Okay. Good. If that wouldn't have happened, if that wouldn't have worked, I would have had to restart my PC, and that would have been very annoying. So when we have a new PLC, I will deactivate all of the safety features here, right? So I don't want to protect my project. It's not necessary. It's for me right now, so I will just deactivate this. This here doesn't really matter what we do. It's for HMI systems mostly, so no password protection. Everything has full access. There we go. So no new settings, like with version 4.0, with the firmware version 4.0, that pop-up that I just flashed through would have been a little bit more annoying. Okay, so let's go. Now, the one other thing that I have already done is I have exported, so there's an export, if I click on this, there is an export button for my tags. So the I/O tags here I can export. I could also import it manually. Right now it's not too much, but I have, since I have them, I have exported them, pressed on this button. They are here on my desktop, and I can import this tag list into my tags here. So I will go on my all tags, and there is an import button. I will press the import button. I will select the file, so you don't need to see my desktop here though. I mean, there's nothing on it, but still. There we go. I get you, Satish. Ring communication for redundancy. I understand. I understand. You had that earlier, but I can't set up any ring network right now. I don't have a simulation for my networking here, and I have a topic that I talk about. There we go. So that's it, right? This is the base setting here. That should be fine. There we go. Why was it so big? Oh God, yeah, I know why. This is gonna annoy me a little bit. So now I want to connect, and I do not use the PLC SIM internal connection. I do use the virtual Ethernet adapter, which is able to communicate to factory I/O. I also need to select all compatible devices because the PLC that we want to connect to does not have an IP address yet. This thing you see, IP address 0000, it's like if you buy a PLC. Trial license, 7 days left, I know. If you buy a PLC, it doesn't have an IP address. Oh, right. Actually, very quickly, while I'm at it, when you download a program, I should open up a different document. I do have a document for this. When you buy a PLC, right, how can you communicate with it if it does not have an IP address? Right? There are many different ways to communicate. If you want to download a program to a PLC, you want to use the TCP/IP. Right? That's a layer. That's a layer that we will use, like the communication layer. I think it's called. I don't have the layer names, but we will use a very high layer. Now the problem is we don't have an IP address. We cannot use this layer. So what happens first is actually we are using the ISO layer, right, or the ISO principle here, to first give an IP address to the PLC. So there's actually two steps when you download the PLC. The first step is using the ISO layer to give it an IP address. And then the second thing is download the program using that IP address. So you can always find a PLC, because finding a PLC happens on the ISO layer, but you cannot always access a PLC because the higher level access happens through the TCP through the communication layer. How's the layer called? Come on, ISO OZ model. What's the thing called? What's the layer called? Sorry, I have that incorrect. Through the transport layer there. Yeah. TCP, yeah, transport, of course. Yeah, there we go. Not too important though, but your PLC has two ways of communicating. And right now, what happens if I click load right now is that the PLC is getting an IP address first. So this is the first thing that's going to change, right? Oh, I can explain software events along the way, sure. I will explain that along the way. So the first thing that's going to happen is it will get an IP address. And you see this? That's the first thing that literally happened, right? And now my PC wants to communicate using that IP address. Now, one thing, my PC is not in this network. My PC is in a completely different network right now. So they have communicated. The PLC and my PC have now communicated using the ISO model. No IP address involved. Now it has an IP address, and my PC itself does not have the IP address yet. So what has to happen on the PC? The PC also has to get an IP address. So make a guess what TI Portal is asking. Does your PC also need an IP address? Yeah, it's an OSI layer, but I didn't know which one. It's a transport layer that we are using now. So if I click yes now, my so far what happened? The ISO layer, right? The ISO they or through the MAC address, the devices, the PLC got an IP address now. Right? The IP address got an IP address now, and and now my PC wants to download the program, but it can't because it doesn't have an IP address yet. So we will also have to give the PC an IP address. Now I can manually do this, or I can just tell TI Portal, yeah, please do so. Thanks to the ARP table. Yeah. Now all of this is a completely different topic, but my PC now has an IP address, which is 192.168.0.241. And now both devices can communicate on the same level, so I can connect now. There we go. Cheers. Network technology, not our topic here, but I just saw it and I think this is interesting. And everything should be fine. I want to download error. What I still have to do is I have to turn on, the PLC doesn't allow to be simulated yet, so I will have to allow TI Portal to simulate. And that's what the compiler says down here. Right. So right mouse button on my project, properties, protection, please allow simulation. There we go. I could have prepared all of this, but now we learned, and that's what we're here for, right? Wait, I'm here because I'm having fun, but I'm also learning along the way. So now I can click finish and I can start my PLC here. There we go. Now it's running. Now I can push the this thing here. I can put on another table, on another desktop or so. Don't matter anymore. Hey, Kevin. I think the name rings a bell, but it's been some time. Congrats on your graduation there. Yeah, some years have passed since since I've been there. But congrats. So good. Now I do have my tag table. I can go online and I can look at all of my values here, right? And I will be able to interpret those. So the set point, for example, that is the one. So that is one of our inputs. We have two inputs. The set point being the first. That's the little knob here. Right? Now I can turn the knob, and the knob I can see is from 0 to 10. And I do have my level meter, which will be our second input. I could also use a flow meter, but I will not. I will use the level meter only. Where the level meter is giving me a value from 0 to my assumption. Currently, I don't know. I don't know. 0 to 10 as well. Don't know. I should know. I should have prepared this, but I don't know. I think 0 to 10 as well. Most likely. I can look this up here. Level meter is in real. It's most likely 0 to 10, or real should be 0 to 1, but that's fine. We will just scale that. So it's 0 to 10 here, in this case. Which 0 to 10 understandable why they did it, but they want to pretend it's a sensor that is sending 0 to 10 volts. Sure, fine, I get it, but I don't want this. Right? Here's what I will change directly. Right? I want to have this thing, the level meter, not from 0 to 10, but, and here it comes, I want to just use what we have here, 0 to 300. Why wouldn't it give me those values from the beginning? So what we will do is a very, very quick, right? And I'm going to just pump everything right now into no, I will make a new block. Function block, sure, why not? Tank, I will call this tank. And I will do ladder, could do anything else as well, but still. And the first thing that I want to do is rescaling. Right. So right now we get a value from 0 to 10. I don't want this. This is kind of in percent. It kind of is correct. But why not? Let's change things up a little bit. And I want to scale this a little bit. So I am going to use this very simple scale scaling process here. Can I? Oh, I need to norm first, sorry. I will need to go with a norming process. So the value that comes in is my fill level sensor. What's it called? Fill level? Fill valve, sorry. My fill valve is going in and it can go from 0.0 to 10.0 right now. Right? And on the output side, what we will have is percentage. Percentage is much nicer, right? So I will call this percentage. Percentage. And the percentage is in real from 0 to 1. That's much, much nicer. So I will make this a real variable. Now we will have a 0 to 1 value. And this value I want to still scale. And it should go from 0 to 300. Right? So this percentage, now we have two things. We have the percentage, and the percentage can go from 0 to 300. And we want this in the level. I will call this level. And this should also be in int. I want this in real as well. Come on. There we go. Yeah, I stopped doing videos like a couple of years back. So that's the first thing, right? Scaling. Scaling is the first process here that is important. And so now we will have the percentage inside the tank and the fill level. And of course, I still have to call this function here in my system. I haven't called it yet. Which is like a beginner's mistake, but I'm rushing right now because I want to do much more. So I haven't done much yet. Good. Right now, tank is empty. Right. NormX, NormX doesn't use hey, Jobran, it doesn't use the Siemens 10 volts. It doesn't use the... you can make it go to 27,648. That is correct. But that would be... Very good point. What Jobran just mentioned. Wait, let me first verify that everything works before I just talk nonsense here. Oh, that's the fill valve. I want the fill... The set point. I want the fill level. How's it called? Sorry, I did level meter. Sorry, that should be the level meter. Huh? How's this stupid level meter? Isn't that correct? Yeah. Oh, and this is a different value. Oh, God, I took the wrong input thingy. Slow is smooth. Smooth is good. That's a good thing. You're right. I shouldn't be rushing. So I looked at the wrong thing. Did I? No, I still used the level meter here. So I looked at two different places. So the level meter here can go from 0 to 10. That's why those three things combine, right? 0 to 10. I will explain, right? So right now, this is where mathematics get involved, and I will open a mathematics thing now. Where is my frickin' folder, please? There it is. Math for... I created an Excel file today in preparation, and I called it Math for PID. So the first thing that we need to do here, and I will get exactly to what Jobran just said. So we do have our level meter. The level meter currently gives us a value from 0 to 10. So the minimum The minimum that it gives us is 0.0. And the maximum that it gives us is 10.0. I will have to use the comma as a decimal point because that's how my Excel is set to German. So I have to use comma. So don't be wondering, please. And I will have this. Please give me a decimal point there. Yeah. So that's a decimal point. This is 10.0. It's not something, it's 10.0. So that's the first step here. Right? That's what we get. Now, what I want in the end instead is I want my level in centimeters or whatever is written on this scale here, right? Where is the scale? There, right? This scale tells me 0 centimeters. Oh, it actually says centimeters there. Until 300. So that is my 0 to 300%. So 0 to 300. That is what I want to have. Of course, this is our ultimate goal, right? That's not the ultimate goal, but that's what I want. So I want to be able to set, hey, go to 150, which is then there. Because that's the value that we have, the physical value that we're going to go to. That is your kilometers per hour. In our case, this is the level in centimeters. This level here, right now, what value does it have? What physical like unit? It's 0 to 10. I don't know. It doesn't. It doesn't have any, like, it's in 0 to 10. The value is, a unit is, I don't know. Right. So the first step that we do, the first step, and now I make a full class out of this. Fantastic. I could make a couple of videos out of this, but welcome to a PID intro class, or analog intro class right now. So the first step that we do is something called normalizing. And I will get to exactly what Jobran mentioned a second ago. Why is it? What is this 27,648? I'll get to that in a second. We don't use that right now, but I will explain what it usually is. Now, normalizing. We'll take the value 0 to 10 and put it into something that is much easier to understand into the frame of 1 to 0. And that goes there. Now, this 1 to 0. This is in percentage, right? It is not 100%, but it is 0 to 1, meaning 0.5 will always be 50%. Right? Imagine the following. If your car goes 0 to 250 kilometers, that would mean 0.0 kilometers is 0% and 250 kilometers is 100%. Or if we talk about temperature in your oven, maybe in degrees Celsius. My oven, I think, can go up to 230 degrees Celsius or so. Right? So this is always our input level. And there's many different ones. So we need to standardize it first. We need to normalize it first. Right? And that's what's happening here. In our case, we are normalizing this, whatever this is, 0 to 10, and we're putting it into percentage. Now what Jobran said, NormX uses something called 27,648, and this would not be in real. This is usually an integer. Now this number is very specific. This number is, some people call it the Siemens 10 volts. Now this Siemens 10 volts, this 27,648 is the same as 100% on an analog input module. Right? If you have a sensor and if you have set your analog input module to go to 10 volts, if you have reached 10 volts, you will get a value, an analog value of 27,648. This is your 100%. Now, if you are familiar with digital technology, then you will understand that this is kind of wrong. Usually, if you have a 16-bit thing, right, you will go up to 32,647? What is... Oh my god, I can't calculate. Calc. That's why I have tools. 1. No, that should be in binary. Whoops. You probably know it better than me. But I will still use my calculator. There we go. We can go up to a value of 32,767. Almost. 767. I mix up numbers. That is 100%. Hey, Malu, I'm good. Thank you. That is usually 100%. So Siemens has something. Their analog input modules from Siemens, they can take up to 114, 4 to 20 milliamps. This would be 4 milliamps. This would be 20 milliamps here, for example. Also another thing, right? And usually 20 milliamps would then be 27,648. Now, why don't we take all of the 16 bits? Why don't we go to the maximum number here? Because Siemens, there is a safety factor. The other way around. No, this way around. There is a safety factor of 18%-ish in Siemens devices. So if you have an analog input module that should only go to 10 volts, you set it to 10 volts, you can go to 11.8 volts. There is a little bit of over voltage, and for the same, if you have current things, right, there is a little bit of safety area on top. Which no one does that. It's Siemens that does it. It's a good feature if you are aware of it. If not, you go crazy. Because this is not 100%. This is 100% for me. This is stupid. Right? Not stupid, but that's what we have. There we go. That's what the 27,000 there is. Wrong button. So we have a bit of overrange, as it is called. I think that is 2 words. In German it is 1 word, but in English it's a bit overrange. There we go. So the first step is normalizing, and the second step is then scaling. Right. With the scale block, right, what I have done here in TI Portal with the scale block is I took the percentage that always goes from 0 to 1. That is what 0 to 1 is, right? It's always 0 to 1 now. Whatever the input is, if the fill level is all of a sudden now 17, the maximum 17.8, right, doesn't matter, because 17.8 is now our 1.0. Right? Now this 1.0, if this is 1.0 now the percentage, so 100%, it will go here, and now it is 300.0. Right? If it's 0, it's 0. Everything in between is linearized. You always use the 27,648 for Siemens, yeah. Instead of 10, depending on, right now, depends on what is connected. If I would have an analog input module, if I would have a literal Siemens analog input module, I would have to go from 0 to 27,648. This is what you usually do if you have an analog input module. Doesn't matter if it's voltage, doesn't matter if it is current. This is what the analog input module gives you normally. But we use a simulation. In the simulation, we get 0 to 10. That's why I'm scaling it, so we have a normal value now, right? Which makes more sense. This is a value that I can work with. Sure. Good. And now you see, I do get the level there as level. Now this took way longer. This whole explanation took way longer. Anything? Yes, this is the scaling process. All of this is just simple basic math, right? We could do this with like manually calculating this, which I will not do now, but we could. Now, this will already help us. Look, the fill level right, now drops, right? Now drops, and I can now see how high is the fill level in the tank right now. I also have a second advantage that we can take, and I can also use the percentage. And let's get to the first. Let's get to the first level of controller here. Right? Now, the first level of controller. Isaac, in this case, the fill level I had to adjust to the simulation. The fill level here is just a real value. Right? It's just a real value that goes from 0 to 10. That's why it is this thing here. I will get to a technology module soon, though. I'm glad, Osiris. I'm glad that you learned it now. Yeah. It is kind of stupid. It's not stupid, but you have to know about it. If you don't, it is what it is. Yes, Lisa, that is correct. We would use like basic math. Like you have a curve and it's all linearized, and But there we go. That's what I have those blocks for. In other languages, I have written this math plenty of times. Why do we use this? Now, one additional comment here, actually, right? There is, inside of legacy, actually a block called scale. This scale block, if I put this into my program here, it does whatever those two blocks do as well, but it always uses a range from 0 to 27,648. If I go to the help function here with F1, it will tell me this is a static value in there. It always goes to 27,648. So this only works with Siemens input modules, not with any other analog values. So you will see it always uses the 27,648. And there is our formula that we can use. So I could just take this formula and put it into my into a calc block or so, which we will not do. We're not here. The great thing, automation, right? Everything is prepared. We just use what we have. There we go. We could make it ourselves, but nah. Okay, let's have the first controller first. Right? So we will have oh god, only 1 hour. Let's see if I can take the challenge here. There's 3 different levels of controller that I want to do now. Or maybe I'll do 3, maybe 2. The first level of controller is called an on-off controller. An on-off controller is the most simple controller. This would be if you're driving in a car with me, right? The on-off controller is extremely simple. It's the most simple kind. Nothing like that. We do something very simple. If we are below the fill level, below our set point, we go 100% with our output. So the pump goes crazy on, just on, right? If we are above the level, we just go off. So this is a simple on-off thing. This is linear extrapolation. Yes, Brett, this is linear that's what's happening in there. Yeah. Which we will not, let's not concentrate on the math too much. Those blocks are doing the math for us. I have written the block plenty of times. There we go. Yeah. So the scaling, that's the scale in the end. There we go. So this is what we want to do here, right? And that's what happens now. Now what we want to do, the first level of controller, is going to be an on-off controller. The on-off controller is very simple. If below set point, output on. If above set point, output off. And there is one thing, if we're exactly at the set point, we can decide if it's on or off. Usually you say, if you are below or equal. And if below or equal to the set point, we don't need to turn the whole thing on. And that's the simplest controller. And let's do this already. Right? Therefore, what was our set point thing here? It goes from 0 to 10. Oh, it would have actually made sense for the set point here also. Like, because the set point goes from 0 to 10, I didn't need to scale the whole thing here. Right? I didn't need to scale this whole thing. I could have actually just used the level meter because it's also on 0 to 10. What I need to do now what I need to do now is to do the same thing actually with my set point as well, which is a good thing. That makes a lot of sense to do actually. Right. But I will now create 2 new variables, percentage level and percentage. Whoops, misspelled that one. 1 second, create this variable, it's real, there we go, percentage level, and I want percentage set point. There we go, got this, got that, and then we have the level here, and we do have the set point. I need to create another one. Oh, no, set point scaled. So you didn't see anything, that's perfectly fine here. For the normalizing block, very good question. Margot, right? Or Mago, yeah. Very good question. That is why you can change the minimum here, right? A lot of sensors, for example, go from 4 to 20 milliamps, right? So you could say 4 to 20. Right? This would now be 0%. This is now 100%. That is exactly why we can change the input here. But very, very good question. That's why we can adapt it. Yes, 10 is supposed to be the voltage. The problem with the 10 as the voltage is that your input, the analog input, we don't have an analog input that makes it into a number. The 10 as voltage, and that is correct, Oliver, is for different tools. Because Siemens uses the 10 volts in Siemens is 27,648. In other tools, it's the 32,000. Right? We could use this, but the physical input module usually changes it into a number, which I have kind of done now. Right. So what the physical input module actually does is it takes this value and it actually goes then from a value there and it scales it. That's literally what the input module does now. Right. This here. Right. It takes the 0 to 10 volts and it makes it into a number between 0 and 27,648. That's what an analog input module does, or one of the jobs. Good. Is there a lot of... This is a basics. This is basics of automation, yes. The scaling process you have in most projects, 100%, yeah. But I'm overcomplicating it right now, right? This is scaled. So now what I want to do is if my set point here, which is the set point scaled, and let's also call this level scaled actually. If my set point scaled is higher than the level currently, completely blast the thing, right? So this is what an on-off controller does. It's the most simple thing we could do. We have a comparator and we say if, what did I write? If below or equal to the set point. Actually, this equal should be here if we are correct. So if we are below the set point, turn the thing on. Most simple controller, called an on-off controller. If we are below, so comparator smaller than, if the current level is below my set point, right, then I want to have the output, the valve here 100% on. And the valve itself is called the fill valve. And the fill valve, you see, can go from 0 to 10. Which is an analog output. This is not great right now, but I will just use this 0 to 10 there. So let's use this. Right? So what I will do is a simple move command now. So I'm going to move a 10 into that output there. Which is not correct. Usually you would now have an analog output. You would have to turn on the analog output 100%. I will just move a 10.0 into the fill valve, I think it was called. Yeah. Now, what I still have to do, if it is smaller than, we want to turn it on. If not, we want to turn it off. So I also have to do the other statement here. I have to push a 0 if we are below, so there needs to be a not in here or a negation. There we go. Hey Malu, they have helped you grow into the automation. That's so cool that I can reach like the rural areas in India. That's so cool. And now look at this magic program going on there. So our set point is currently set to let's set it to half the tank ish. So set point is right now at 5. So you see the set point we want to reach right now 148 centimeters or 149. And you will see we are now above that level. And we will now keep that level as well. Right? See this? We will kind of be stable at 150. Kind of. Not 100%, You watched every video? Oh my god, isn't that like 300 videos or so? Good job, good job. Or 100, I don't know how many videos there are. But I'm happy I could help. But now we have this. This is the most simple kind of a controller. Good job. Good job, us. It only took an hour. Now programming this in a professional field, of course, this is like a 5-minute job usually. You don't even need a controller for this. This is just 2 sensors, right? If one sensor is higher than the other, turn it on. This is just this most simple like thing, right? But right, I'll leave this on right now, and maybe you can see a problem with this. Does anyone see any problems with this? How long have I worked in automation? I work more in education itself, but in the field itself, I have worked for 16 years now. And I apparently can't drink. Is that visible on camera? Yeah. So I'll just do this. Does anyone see a problem here? Like imagine this is you driving a car. You want to keep a steady 150 kilometers per hour, right? But this is what happens. Any problems? Huh. Oh god, I can't. Now I have this. Now I have a stain. I can't drink. Sorry. Yeah, probably there's some delay here going on, right? It will keep going on and off. I mean, on and off is kind of okay. There is no hysteresis. Tim already going on here with the correct wording here. That's fantastic. Constant valve operation. That is the most important thing even. Yeah. Moving 10 means fill. Yes, moving 10 means fill. Yeah. It's splashing, right? It's splashing. How to break the valve in 2 seconds? Yes. It always just gives peak. I play, like, Shinwisey, I do play games on my Twitch channel with the same name, right? Yeah. So we have many problems here. Right? When we reach the set point, the input flow needs to be the same as the... Yes, Jasmine, that's exactly where we want to go. But that's what we have. We also overshoot quite a bit. But this depends on the system. It could be a very good controller. The 2 biggest problems that we have now is the valve operation here is just on-off. In your car, that means you step on the gas full or not at all. Right? Full, not at all. Full, not at all. Full, not at all. Full, not at all. In the worst case, and this is a good case right now. This is even a good case right now. In the worst case, this will lead to your system doing this very fast. This right now is slow. The valve can take it. This valve can take this for months at least, right? But it will lead to many, many hardware cycles. Yes, 100%. And if my system would be faster, right, which I think I can actually increase the speed here, right? If my system would react faster, right, it will create much more rippling. And I can't do that, unfortunately. Right? It will create much more rippling and wear on the actuator. Right? This controller, for many, many reasons there, could even be from Romania. Hey, Vlad. This controller is also called a bang controller. Right? A bang or a bang controller, because it turns on and off very aggressively. It's for 5 years. I've been not doing it for 4 years. So I've been basically a YouTuber for a year, you can say. Right? Very aggressively. It can, however, be a very good controller. Depends on the system. Right? It highly depends on the system. Yeah. But not the best right now. So I already read like a very good comment there from Tim. Right? Tim, a gorilla regulator might be as well. Yeah, very yeah. Very aggressive. There's many names probably for it, but I know it as bang controller. We could add Anna. Yes, we could add a bang hysteresis. I wanted to do so much more today. Oh god. But yes, let's improve this. This is our first controller type here. Right? And now what I will do is I will go offline and I'm going to add a new block. I will make this a function. Let's make it a function block, doesn't matter. And I will say this is an on-off controller. And I will do something that you should not do in most cases. On-off controller, right? In most cases, you do not, like the song Bang Bang, yes, you should not do something called a conditional call, right? What I will still do is I will put my on-off controller actually inside the tank here. I'll put the call of the function inside of this, make it a multi-instance, whatever that is. That's a different topic. Why? Okay, interesting. And I will cut this and put this in the on-off controller here. Hello? Cut and paste. I can't cut and paste. Why can I not cut and paste? Come on. Let's see. So I will cut the whole network now. Put that in here. That works now. Level scaled and set points. I will not have another. I will not put it in another network. Doesn't matter. This is not too much effort for me to do. I would usually make this in another, like in a function block itself, but we would have to have many in and out parameters. I don't want to do that. Right? So what I will do instead is library. Right? I'm going to oh, I can just deactivate the whole. No, I can't. Shit. What I would have to do is hey, logical controls, hi. Let's do something that is not really... It's not good. Don't ever do what I'm doing now. But I will just do a simple jump instruction. That's not what we should be doing, but I will just do that. Yep. So afterwards, we will jump, and we will not use network 3. So jump instructions are actually quite convenient. So you can skip things. This should not be possible. Yes, it is. On off. Yeah, on off. Doesn't matter. Hey, Gordon. Hi, how are you doing? So we have the on off controller, so we can jump here. Right? With a jump command, you can jump to another part in the program. So right now I can choose where I want to jump. Right now we use the on-off controller, so I want to jump to the on-off. Right? Now what I can also do is I can go and make the next type of controller, which is a so-called 3-point controller. That's what a lot of you have already discussed, right? Or mentioned. Now with 3-point controller, oh, don't get joy. You want to know now the difference between a function and a function block. Not really going in there. A function block has an internal memory, which right now everything could be a function. I don't need a function block right now, but yeah. Glad to see me. Hey, thank you. Glad to like read you every week. Okay, so now this is right now my on-off controller. Now we want to also have the 3-point controller, so I will put a label here, make this 3-point controller. And the 3-point controller can already improve our system. Now if I say 3-point here, we are skipping this network. Right? That's what the jump command does. Not really what we should be doing, but I will just do that. Now in the 3-point controller, right, we will do a couple of things. Hey, Brad. You can do the auto-tuning. You can also do manual tuning. There's a lot of math involved, but my favorite is the CHR tuning method. Right. CHR. Oh, CHR, of course, is a car as well. Are you kidding me? The Hirnronsresvik tuning. You can manually... It's just a little bit of math. It's not even complicated. So let's see. So 3-point controller. Now what we need to do in a 3-point controller is I will need a new variable, and I'm going to create a new constant variable here. Now this constant variable is going to be my so-called tolerance. So right now I try to keep the level exactly at 150. That is what we have. Now with the tolerance, we will move this a little bit and we will have 3 points. We have the set point where we want to go. We have a lower limit and an upper limit. So we slow down. There's also Ziegler-Nichols. The ZN method is another method for tuning. They will have the very similar results. Yeah. But auto-tuning does those. Auto-tuning does those methods, actually. I don't know which one, but it does. One of the standard methods. Now, the tolerance here is in float. Real. Sorry, wrong programming language for a moment there. And I can just say, hey, if I say the tolerance is 0, then my upper limit is 150 and my lower limit is 150. But I want to have this a little bit, like a tolerance of maybe 10.0. Right. Did I type 10.0? So a tolerance of 10.0. So I will have a lower limit and an upper limit. Right? So we will change this here just a little bit. Right? So we will need to calculate first, though. We will need to calculate those limits, so it's a bit more complex. And I can definitely not finish anything that I planned for today, but that's okay. Add and subtract. 3-point controller, calculate the limits. Now those limits, turning on if we are very low, turning off if we are very high, those are also called hysteresis, right? Because we're going to move between those 2 points now. That is what the hysteresis is. Now, the upper limit, and we will have the lower limit. Right? It's always the set point, and the set point scaled. Yeah, set point scaled. Plus our tolerance. Right? And the other one is set point scaled minus our tolerance. Now this gives us many, many advantages. Right? Like, for example, our controller, our system doesn't turn on and off as aggressive anymore. Right now we don't see the aggressive too much, because it is still like, it's still a fitting controller right now. And it's already moving between those. But if you have a very fast system, it will be very, very, very like aggressive. Right? But right now we will have an upper and lower limit. How many programming languages do I know? I don't know. Depends on the systems. 10 might be low. It doesn't really matter. Oh, by the way, if you ever get this message, the specific call environment is invalid due to programming. Oh yeah, I closed the block and you can reopen the block. And this library doesn't. I don't use that anymore. 1 second. You just close and reopen the block. 10 might be low. I'm just making up numbers now. Right? But we have our lower limit, our upper limit. Right? And you see they are now 158 and 138. And now what we want to do, of course, is turn on and off. That's still the thing that we do. Still turning the thing on and off at 100%. So we need this still. So I'm going to take this. But right now, not directly looking at the level, but looking at the lower limit and upper limit. We want to turn on if we are below the lower limit. And that's what goes here. If we are below the lower limit, and that was the, what was the thing? Set point? No, the level scaled. Right. And we want to turn on. That's when we want to turn on. And if we are above or equal, right, the higher limit, we want to turn off again. There we go. I hope I didn't make a mistake. Maybe I did. Probably even. Can I get a short summary? I mean, you will see the summary in a second. Which a project about project structure. I have that on my list already. Thanks for being an important resource for the Danish engineering program. You're very welcome. And now you will see we turn off. Okay, right now we're turning off. So we're letting liquid out of the tank because we are above our upper limit. Right? And we will have PID as the next controller. So I still can go in there. Right? And right now, this is going to take ages, but that's okay. Right? But we will move between our lower and upper limit now. And this is hysteresis. If we come from the top, we go to the lower limit and then we go back up. And then we move between this. Oh, now I want to show one more thing. I will get into the PID parts. Oh god, it's 40 minutes. I want to show you one more cool thing. Okay. Shit. Oh, 2 hours is not enough. One more cool thing. Right now, I'm talking, right? I'm showing and I'm demonstrating with my fingers and with my hands. Why am I so stupid? I can just take a so-called trace. A trace is exactly what we need right now. I want to add a trace. Now, a trace, and this is probably not new for everyone, but this is something really cool. In a trace, what I can do is hopefully I can take shit. I can't take shit, but why? Oh, it gotta be static now. God damn it. I will have to make a smaller change, which makes a lot of sense. All of this needs to be static now. Doesn't matter, changes nothing. It changes stuff a little bit, but it doesn't really matter. Needs to be static though, so I can actually get that. Now what I want to do is I want to display all of this in a graph. Traces are graphs that do exactly what I just told you, right? If I set up, I just added a new trace. Right? Now in this trace, what I want to see is right now the lower limit. I want to see the upper limit, which is my tank data block here, upper limit. And I also want to see, what other variables did we have? Percentage level, no, set point scaled. Yeah, the set point scaled. And I also want to see the current fill level, right? Set point scaled and level scaled. There we go. This is a 2-position controller with hysteresis. Yeah. There we go. Now I do have those, right? Those are the values that I want to record and display. And what I can do now is click this button. Yep. And I can click on live. And now I can see it live. Now, can I overlay them somehow? Shit, can I? Okay, does anyone know if I can overlay them? Damn it. One second. Interpolated view. Save the current display options and add. What? No, not interpolate. I mean interpolated display samples. No, what? Why is it just fat? Love it. Can I just see all of those overlaid, please? Formula, color, scaling group. No. Automatically. Just 1 second. Just 1 second here. Minimum scale. 0, 2, 500. 300. One second. Scaling group, probably. Just 1 sec. I need to test out this a little bit as well. Set group to 1. That's what I probably. Yeah. Yeah. That's what I thought. Thank you. And now I don't want this anymore. So now, let's take this in minutes. And right now the thing is, we are monitoring right now, and we see this in minutes, and this is kind of, right now it is kind of stable. The thing is, the level is what we currently have in the tank, Why is this? Oh, wait, I need to zoom out. This is not pretty. This is not pretty. It doesn't matter. Now, if I set the fill level here to 0, let's set the fill level to 0 right now, a little bit. Right, which I can do with the reset button here. Now, this is 0 now, the fill level, but also my set point is 0. So I will now change the set point, and we can then see how the controller behaves. That's what I wanted to do. How do I do this, that this is supposed to be a minute or so? It doesn't matter. It should be fine, hopefully. So I'm now setting this to like 50%. And you see the brown one here, right? The brown one is our fill level. Scale between, it doesn't really matter. Let me zoom out. Damn it. And you see the brown one, the fill level goes higher and higher. How do I zoom? Sorry. No. 0 to 500. Thank you. Now if I reset it again, and I'll put the set point there, right? Goes to 0, you see everything is rising, and now I don't know why it is. I can of course zoom out. Yeah, oh, if I stop, it shows the whole history, you're right. That's a good point, Silent Sniper, thank you very much. Yeah, but now it's rising, right? It's rising, but it only shows, no, it doesn't show the history, because I'm not saving it anywhere. That's the problem. It just has this much of a display. I think I can't even zoom out. No. But now the controller, the brown one, and that's what we want to see. The brown one wants to stay at the green one. That was our on-off controller. But the brown one will now stay between the red and the blue one. Not exactly, because the system is a little bit slow, but it will turn on when we are below the red one, and it will turn off when we are above the blue one. So we will have this behavior now. Now, if I want to have this pretty, so the stream itself will be recorded, the values not. The stream you can always watch later on as well. Now, let's make this pretty. God damn it. Let's actually also, yes, let's make it pretty. 1 cycles, I want to have, that's approximately 2, let's make 10,000 samples, which is approximately 10 seconds right now. I want to trigger on a tag. The tag is if my set point scaled is inside a range, and I will set this range from 100 to 100.0 to 200.0. I don't want to use max, because that could be very long. Oh no, it's 21 seconds, but I want to use 10,000. To do it correctly, now you're run. Now I'm rushing. I can make an organization block. This organization block is a cyclic interrupt. The cyclic interrupt, I will give this a 1 millisecond, right? And I can use this 1 millisecond block now. Right? I can use this 1 millisecond now, and now I can set this in seconds. So I want to record exactly, and that's what I had beforehand, 10 seconds. There we go. The value must be greater than other way around, of course. There we go. I want to have the pre-trigger of 1 second. Why did I set this to 300? I want 100. There we go. So now if I put the set point between those values, the device will take recordings, and we can watch those later on. Here we go. That's it. Okay, if I did any mistake, this was just me fooling around. No, I need to upgrade my... My PC is very fast, Luca, yes. So now I'm downloading the trace, and I am also recording now the trace. And right now it is recording, so we can look at the values later on. But what I want to do is, what I can do now is I can close this trace, right? I can go offline, I can close the trace. And now I can play around with my system here a little bit. So now I will set the set point to like 150-ish. And I will see how my system reacts. And now I think 20 seconds or whatever I set the thing to is too few. It takes longer than 10 seconds, so the recording will be messed up. Doesn't matter, we will have separate set recordings. So let's make another point here. God, why? The perks of being a gamer, yeah, I do have a fast PC. The perks of, like, no, I also invested in this because of TIA and automation stuff. And now this will be between those two values. It will pop back and forth between those two values. And now what I can do, because I set the trace, and I should have set the trace to like 30 seconds or 2 minutes, doesn't matter though. I can look at the trace, like at what has happened inside of the device, you see? And now we should be able to see at some point, and because I'm just taking like 10 seconds recordings, you see that the thing is like falling and jumping back up, right? Depending on if it is above or below. You can see it perfectly, and I won't do that too. Installing TIA on SSD, definitely, yeah. Now this is not perfect. Last thing, and then I will. Okay, I will change the settings here for a little bit. Record every, let's make this, I don't know, every 10 milliseconds. And I want to record for how long will this probably take. Let's make it 1 minute. Is a minute enough? Yes. Let's make 90 seconds. 90 seconds should hopefully be enough. God damn it. Version 20 is also going quite fast. Yeah, TIA version 20 is quite fast as well. But you still need to have pretty decent hardware. So right now, let's go back here. Let's reset the simulation. So I reset the simulation. The set point is now 0. And now I want to start recording, which it is waiting for the trigger. The trigger is me turning on the set point here. And then we can hopefully see the magic happening. And I hope that 90 seconds is enough. If not, then I don't care. There was one more setting that I need to, it doesn't matter. Right now, I turn it on. And now it is recording. And now we will also have the display for 90 seconds. And I can't put them all in one scaling group again. Oops, not 11. And now we see it. 300 is the next one. Right. So if we go above the blue one, right, it will turn off. And let's maybe zoom in a little bit. Right. And if we go below the red one, we will turn back on. That is what the 3-point or a 2-point controller, I think it's called 3-point actually, but that is what our controller right now is. Right. That's what we're doing. Now this is what we have created. Even with a trace. Hey, we have added the trace. Yeah, every 15 minutes becomes a 3-hour project. I mean, it's been, yeah. You're right. There we go. Now this is pretty decent. This is pretty good. Yeah, they have some nice features in PSC Sim version 20, but it gives me a lot of errors as well. But always can happen, right? This is good. This is already a good controller. This is decent, I would say. Not perfect, but decent. Hey, Brett, I will rewatch tomorrow. Go to bed. Philippines, then. Wait, isn't it early? Shouldn't it be early right now where you are? But good night. I'll see you. See you in the review there. There we go. Right? We have this nice controller now, which isn't perfect yet. This is definitely better than what we had in the beginning. There we go. Why does it not keep the scaling groups active? But you see, we're keeping like a semi-constant level. That's good. Now there is one way better method, and I wanted to develop this whole thing. And that's why the title of the video is, I think, is math related to programming? We have done a little bit of math now. Not too much though. The real math would start now. And now is the fun time. So far I've been just not fooling around, but this is definitely stuff that happens. You do have those controllers everywhere. They're quite cheap, they're easy to do, right? It's not PWM control yet. Not yet. I mean, on the long term, yeah, but not really. PWM will be the next type of controls that we have. PLC Sim works with PID blocks. You have to use PLC Sim Advanced. That's why I have set this here to TCP. I hopefully, if not, then I don't know. That's why I've set it to TCP/IP single adapter. I think. Maybe I'm wrong. I will find out now. The next live is every Tuesday, same time. Tuesdays, 6 p.m. That's when I'm streaming. Good. Next controller will be our PID controller. Now the PID controller is much better. Much better, but it's like poof. Of course, adds on a lot of complexity. We have one thing that we currently are doing that is completely strange. Hysteresis is kind of a slow PWM, but the PWM, Emily, gets into, or Emil, I don't know, sorry, it's hard to see. So the thing is, the PWM would be more on the output side here. Right now, our fill valve is not PWM controlled. It kind of is over a longer term, yes, but right now it always turns on and off fully. Always 100%. It doesn't know like, oh, I turn on a little bit. No, right now it's completely off. And in a second it will turn completely on. Right now. Turns on completely. It doesn't know anything in between. So what we could do instead is, of course, control the fill valve and make it much softer. That's what the 3-point controller could already be doing. I could already be softer and I could say, maybe 10. 10 is too aggressive, right? And 0 is also too aggressive. I could say, maybe keep it open a little bit, maybe 1.0, and don't open it so aggressively. Open it maybe 5 points, maybe only half, right? Yeah, this is not a possibility. I could do this, but I would do this manually right now in my program here, right? This would already be much softer now. And this is what I want to, the output is what I want to PWM control, like the value. I have this analog output. There are two different types of PWM. One is time control, and the other one is, like that's the one that we have now, and the other one is value control. And I could value control this. You see, right now, because I'm letting still out 1.0, the tank doesn't as aggressively go down anymore, the fill level. Because I'm using 5.0, it doesn't aggressively go up anymore. It's much softer. So what I would do over a longer time, of course, is I would find better values. 1.0 is too soft. Maybe make it 1.5. And maybe make the aggressive one 3.0. Right? So I would try to find good values that are not too aggressive here, that are still fast, but not too aggressive. Right? Random question. Codis is good. Codis is good, yeah. I haven't really worked too much with it, but I know it's big and a lot of people use it. That's why I would say it's good. If a lot of people use it, it must be good. Doesn't have to be, but usually is. So right now this is not as aggressive anymore. So our system is much more stable, much nicer. Right? Now what we want to do is I could always now permanently monitor this And I could manually, not with the PLC right now, I could do this with the PLC, but I can manually take my fill valve up here, and I can manually right now try and find a good value for this. Right? Maybe 2.5 is great to keep a constant level. Like I could manually change this up, right? Yeah. It's a bit pulse amplitude modulation. Yes. Right? I could manually, right? I could manually do this. This is what you do in your car. Right? You don't go 100% acceleration, 0% acceleration. That's not what you do, right? You go like in the beginning, like you go soft on this, right? A little bit more, oh, a little bit less, a little bit more, a little bit less, a little bit more, and then you try to get into the correct point, right? And that's pretty normal. That's what we want to do. And that is what a PID controller also tries to achieve on a mathematical level. Like I can test this out and I will find out a good value for me, right? And this has 3 parts. The first part is a proportional part. Now in your car, if you want to go to 200 kilometers per hour, which is totally legit in Germany on the Autobahn, yeah, and you start at 0. You start at 0 and you want to go to 200. What would you do in the beginning with the gas? Step on it strongly, right? You would go very strong on it. And the closer you get to 200 kilometers per hour, the less gas you would give, right? The less acceleration you want, right? So the closer you get to your point where you want to be, right? The less you want to act with your controller. And that is called a proportional controller. Proportional to the difference here, to the error that you still have, you will react stronger. If the error is 100% of the maximum, you will go full gas. Right? You will go full gas. If you are at the point, you will go 0 gas. Right? You will go like you will not accelerate at all anymore. So the stronger you have to accelerate, the stronger you want to accelerate. And I don't drive like you probably. Yeah, that's I'm a very what's it called? I'm a not scared driver, but I'm cautious. I would say I'm a very cautious driver. So what we need for this, guys, right, is the first part here. The first part would be the calculation of how far are we away from the set point right now. How far away are we? Brings me back to control systems. That's exactly control systems. Yes, that's 100% what it is. Like, how far away from the error are we? From our set point are we? So it's a simple, a simple, what's it called? Subtraction. Yeah, subtraction. Oh God, my English. It's a simple subtraction. So this is the first thing that you do, that a PID controller does. So I will now have a PID controller here. This will be PID. Jump level doesn't exist. I know. There we go. We can use depending on your system, Orgidai. Usually you use an optic sensor. Usually you usually have an optic or an ultrasonic sensor. But you can also use a pressure sensor. Depends on the level design. Yeah. So what we calculate here usually is the error, right? It's not like an error. It's just the value, how far away from the set point are we right now. Right? And this is, of course, a real value. And we will calculate the error from our current level, our current set point minus our current level. So the closer we are to the level itself, the smaller the error. So right now we are almost at the set point, and you see the error itself is rather small, but right now the error is getting bigger. Right? And you see the error is getting bigger and bigger because right now we are moving away from the set point. Right? You see this is dropping very slowly. Right? This is dropping very, very slowly. But we are moving away. So what we would do is we would now try to be more aggressive, right? To act stronger on this. Right? Fire is perfect. Like of course, that's what we want to achieve. Each part has a different purpose. Now this here could go to my output, so to say. Right? Now there is a lot of math involved in this, and I basically only have 15 minutes left that I wanted to stream, so I'll maybe take this into a second session. But now is the interesting part. I can take this and put it to my output. The problem with the output right now is that the output, where is my output? Yeah, the output goes from 0 to 10. So if I would push out and I would put 0 to 10 again. If I would now put out the error directly here, that would of course be a big problem. This error right now, putting it out, that would basically just be an on-off again. So what we have is we need to rescale everything. Now it's full math. I'm not going to do a full math class now. I planned on doing a little bit, but not really. Right? We do have the error, and the error itself has many parts associated to it. One very important part. Thank you very much. One very important part is the maximum error. What would be considered 100% error? And the maximum error in our case, and I will do some calculations here, the maximum error. The maximum error, and that is a long reel again. Oh, a reel again. Now the maximum is of course our, not the level. The maximum error is of course from 0 to 300. So the maximum error would be 300.0 minus 0, which is kind of stupid but right now, but there we go. That's our reel. So the maximum error. Important. This is just important stuff. I think that's what we have to do now. That's our maximum error. You can always ask questions. Hey, Coit. You only make it for last. Jason, it's gonna be like 15 more minutes today. I still want to finish like a little bit of this. Okay, now, right? We do have this. Right? Now, why do I need the maximum error? What I want to do is, and what happens is in a proportion, and we would go with a pure P controller first. In a pure P controller, right, you want to go, of course, the strongest if you have the maximum error. You want to go the weakest if you have zero error. So that is important here. That the difference between those two is now important. It's all math. This is like the saturation limits. Yes. Now, another important thing in this is that you have something called the proportional, like the value, a multiplication value. Now, this multiplication value I will put in as a constant. God, this is right now. This is gonna be too much. Like this is, if you phase out perfectly fine. What's it called? P. Not multiplier. It has a name. Yes. Yeah, blah, 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 components. No, 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 no. It has a name. Uh, Damn it. What's it called? It doesn't matter. The gain, proportional gain. Thank you so much. Yes. The proportional gain. Thank you. Ah, phew. Thank you very much. Now, the proportional gain is an important factor. I will not like go into the most details here. But if we set the proportional gain to 1, this is a multiplier. Right? If the error right now is 300, which is our maximum error, right? Our output will be on at a maximum, so at the 10, right? If I have this at a 5.0, right, the output will already be on, right, to 100% if we have 1/5 of the total error, of the maximum error, so 60. Right? So this is an important factor. It's a multiplier. Yeah. It's a multiplier, but it's usually called gain. Yeah. Right. So right now, if I have an error of 60, which I currently have, and a gain of 5, our output will be active at 100%. And it is, of course, limited at 100%. So what I will have to do, and thank you everyone for the answer there. Sometimes I also like words. Thank you very much. Now what I have to do is, of course, do more calculation here. But that is what I will put in the next network. The proportional part, I will call it. Now, for the proportional part, oh my goodness, I have 10 minutes. I can never ever finish all of this. Now, for the proportional part, as I said, we will need some mathematics. We will need to see. We will need to multiply, of course, the current error. Right? The current error will be multiplied with the proportional gain. And I probably will make a mistake, and I'm sorry if I do, but now I'm really rushing it. So the current error will be multiplied with our proportional gain. And this is now for our controller, this is the proportional part. How strong is it going to react on the error right now with this proportional part? Proportional, I will call it proportional reaction, which is not 100% correct, but I will call it that. This is now also in real, right? And this is the proportional reaction. Now this proportional reaction right now is 5 times the current error. What we will need to do is it will still need to be limited in between 0 and 300. Right? Yeah, we will, exactly, we will. And is it Emil or is it Emily? It's Emil probably, right? Yeah, we will still need to scale it for the output size, 100%. But what I need to do first is right now, I do have a little bit of a problem because this proportional gain will now make it to a higher error, right? We cannot go above 300 because 300 would be our maximum, right? So we want to have the maximum reaction if we have the maximum error. There we go. So what I need to do is I will need to limit this value now. This can only be between 0 and 300. And therefore we have the limit block here. So I will take the limit block. I will take my proportional gain, put it at the input here. My minimum is 0.0 and my maximum is 300.0. Now this limitation could happen at different points, but I want to do it here. P limited, I will call this. Now P limited will now be between 0 and 300, I hope. If not, then I don't know. The Mohammed, the recording will be saved, yeah, and the program as well. So right now you see, if we have an error above 60, the system reaction should now be like at a maximum, which it is. Right? 300 means we have a maximum system reaction. Now, if the error is smaller again, which I will now make, right? The system reaction will also go smaller. Okay, perfect, Emil, then. Thank you for your assistance here. You are now my official TA here, my teaching assistant. So you see, right? Right now, this value here is important for us. What we need to do with this is if this is 0, our system should not react at all. And if this is 300, our system should react maximum aggressively. All right? If I did the math correct. Yeah, I probably did the math correct. And let me, before I read the comments again there, sorry, let me do this because I don't want to make a mistake, because what we need to do now is we need to scale this on the output, of course. Right? And therefore we need a norm and scale again. Ugh, so annoying. Norm. So I will need to normalize this from 0.0 to... So this can go from 0.0 to 300. And the value is the P limited that goes in, and the output is then in percentage, and the output right now should go on. I will give this just a temporary value. Temp P, I will call it now. This is so messed up, my variables now. This is just a real. I don't need a long real. And now the block is quite wide. And this needs to be put on the output. And if you remember correctly from earlier on, the output is from 0 to 10. So now I will need the scale block that goes from 0 to 10. Whew. I can't finish it. We have 5 minutes. The I and D part are not complex at all. They are. They are even very complicated. And I will put this directly to the output now. Now temp P scaled. Oh God, this is now a mess. And this I want in real again. And this will give me the output here. Right? And I will just push this directly to the output. I want to have this pump power or so. It's just a valve. Valve opening. And this valve opening is just a move command now, and the move command will just directly take this value and put it on the valve. And then we will have a P controller. Valve, what's the valve? How's the output field valve? There we go. Now this is a P controller right now. Hopefully. It probably isn't. We'll see. So right now, the closer we get... Why isn't this... Oh, I'm forcing it. The closer we get to the... to our set point. So I'm going to put the set point now to 150-ish. Right, to half the tank. The closer we get to the set point, the less our valve should be open. I'm still forcing it, so I'm short-circuiting it. So now I will release it. And now we should get a nicer reaction. Hopefully after watching the video, PID drops. I just started with the P part and Hey Mohammed, thank you for welcoming me back. So this should be getting thinner and thinner. You see this? The reaction gets thinner and thinner the closer we get to our to the maximum here, to the to like our set point value there. There we go. Whoop whoop. So this works. This is now a pure P controller with a proportional factor of 5. Now this has several issues right now with it the thing. Can I... Jason, very good. That's the most important one that I want to talk about. That is very, very important. That's why I'm going to make another trace. Hey, we talked about traces, and I'm going to make a new one. We do love traces, don't we? Now, one problem that this has, and you are 100% correct, and that is the main problem with a pure P controller. And I should not have clicked on recording. I want to stop this, damn it. Yes, der stehende Fehler. Stationary error, steady state error. Yes, yes, yes. Steady state error does not always remain. But you're right, Pranav. We have the steady state error that will remain right now. Very good. So let me just change the trace here a little bit. So we don't need the upper and lower limits anymore. They're gone out of the window. Right? We do have our set point scaled and our level scaled. I do need those two that I want to monitor. And I also kind of want to monitor the strength of the P controller here that I called the strength. No, I can take the fill valve. I can take the fill valve because that is our strength. We only have a pure P controller, so I can take the pure P control, the pure output here, which is the fill valve. Why can I not take this? There we go. Not perfect, but that's what we have right now. So I am going to record this for like, this is going to take longer, 120 seconds. Maybe 2 minutes, maybe that is enough. Right? And I want to record when I have the set point there, perfect. That should be fine. And now I want to download this. And as soon as I click recording, I will reset this thing first. Right? Ugh. Why is nothing happening? Oh, because the, because that. Okay. Hey, Engineer Kirsch. So what I will do is as soon as I put the set point on a higher value, the trace should start tracing. Let me download again. I'm not sure if I did. Download and activate the trace. It's not tracing right now. The maximum error is for my math calculation. I can explain again, but I need it. Like it's internally needed right now. So if I set the set point, now it is recording. Right. And I'm going to look. We have to wait for 2 minutes to look at the recording. And now it's 8 p.m. Oh, you will never see the result. I'm going offline now. Bye. No. We will still see this. At least I'm having fun. So a little bit more is fine. Yes. There we go. So this goes up. I should make a PID video about this. This would be great for explaining PID. And you see, this is getting smaller and smaller. Right? It's getting more slim because our P, the closer we get, I'm not leaving it. Sorry, the closer we get to the to our set point, the less the P factor is going to react. Right? This is now the steady state error. Right? And the tracing is happening. Ooh, this looks great. This is just how the controller should look like. Right? This is so good. This is I should be teaching automation classes. I should be teaching, what's it called here? Process control classes, because that is what process control is, right? This is, I'm gonna make a video out of this. Yeah, you see, we didn't need to make 2 minutes is too much, right? Our system doesn't even do much anymore. What we can see is, and I'm going to put the first and the second in the same scaling group. No, scaling group 1 and scaling group 1. There we go. Right. Now what we can see, look at it. Oh, this is actually fantastic. I love this. This, like how this looks like. I love it. I can't do. So what we can see here, right, is the green part. The green part is my set point. I was fiddling around with it. And now was the 2 minutes, of course. There we go. So I have to put them both in the same group again, I think. Yep. 1 second. 1 and 1. There we go. So the green part here is my set point. That was 0 in the beginning, and then as soon as I set it, my system wants to react. The red part is my system reaction. And you see, for a long time here in the beginning, the system reacted at 100% strength. The closer we get, though, to the error here, to our set point, so the brown one is our fill level, the closer we get to the set point, the less our pump is going to react. until we have almost reached the set point. The pump, though, is not going to act stronger because it's not supposed to. Right? It's not supposed to get closer. Our math is done, right? So we will have this difference here. Right? we will have this difference. And this is called the steady state error. We will have this difference forever. It is going to be there, unfortunately. Now, there was a question, and this is what a pure P controller is designed to do. Now, one thing we can do to avoid this right now. Two things. The one thing that you would do is have an integrational part. The integrational part would react on all of this over time. So it would try right now to go stronger because it realizes, hey, I have not reached my set point yet. I have to be stronger. Right? That's what the integrational part would do now. It would over time act stronger. The P part doesn't care. Right? That's the first thing that we could do. Now, the second thing that we could, and that's what you would do, of course. The integrational part would be to counter this problem. Now, the second thing that we could do, oh, this is going to be fun. The second thing that we can do is I do have one value that I can play around with and one value that I can change. And it's this one here, right? What would happen? Not just hypothetically speaking, but what will happen if I turn this, for example, to, I don't know, 50? Well, 0.0, of course, sorry. What happens if I put this to 50.0? That would mean my proportional part would act stronger. Right? So we would make this smaller here. Right? Now the jump from 5 to 50 is very aggressive. That is way too much. Just wanted to emphasize on it. Let's take a value that makes a bit more sense. So let's make this maybe 20.0 again. Right? If this is now 20.0, right, you can take guesses, and some of you definitely know, right? What is going to happen? And with 20, I don't know. Maybe I'm mistaken. Maybe it's not aggressive enough yet. Maybe. So I'm going to reset this thing, right? And I do think right now a trace is probably going on. Yeah, so I will stop my trace recording here. And I'm going to, so this was the trace here. This is stupid. So this one here is the trace with P part of 5. I can't rename it. I thought I can rename it. So this was here with P part 5. Can't rename it. Okay. Why does it look like shit? Doesn't matter. Oh, this was me turning it off. Now another one is now the one with the P part 20. So I will start recording and I will now wait for the trigger. So we have to wait for 2 minutes here again. So I should have taken a screenshot. Damn it. Doesn't matter. Now I will put the set point higher here and this should start the recording again. Yeah. There we go. And now this is going to record for 2 minutes. Yeah, it's starting the recording, and then we will look at the recording. But now I can read the chat finally. Adaptive gain, not gonna. Not right now. This is not adaptive gain. Not gonna happen. All right, to the physics behind them. Oof. Where I had PID in school was actually in the physics class. I can give advanced topics in TIA, yes, but not right now. Yeah, I do. Like if I drive a car, P gain is also for me like 10,000 maybe. The measurements are stored on device cutter, yeah. I can copy the. Oh, I could copy them into the project. You're right. Let's see. So right now, ooh, no, this is actually quite nice. 20 is not enough. But look at what happened here. At this moment, you see this? This moment is very interesting. I mean, relatively speaking, interesting. But this moment, we had a little bit, and it's not in the measurement here. We cannot see it, unfortunately. But we had a little bit of a strange system reaction here. So what I will do again to emphasize on this, and this is a nice controller right now. What I will do to emphasize on this is I am going to increase this, and let's make it 50. Because I want to emphasize on... I want to see the result, and I want to emphasize on it. So let's see. Critically damp water tank. Yeah, this is all completely unnecessary right now, but that's fine. So let me stop the recording. Let me delete the trace here. I should have saved them in the project. You were completely right there. Who said it? Keddy, I think. Yeah, I think I needed to save it. Yeah. But it's whatever. Did I download the program? The live stream will be available. It's all available on my channel. I never delete anything. No, I deleted some things in the past, but nothing that could be useful. So I'm now starting my recording here again. So now let's go with the 150 set point here again. Oh, Pranav. Yes, that's a good word. That's the word I'm looking for. Right. There we go. Hey, Dennis, imagine my side of the story. Imagine for fun and entertainment, I am doing a live stream on control theory. Imagine my side of things. Oh no. But you're right. Yeah. Yours is not good. Mine is worse. This is kind of a good system though. Yeah. But what you see right now, right? And this is what I wanted to provoke. You control the biting point. Is it the biting point? Schleifpunkt in German. Schleifpunkt. But yeah, you're kind of controlling that. Yeah. So right now, what is happening here in the system? Oh, this is actually a very good example. Do you see this? What's going on here now? What is this now? Oh no, what we have achieved is something quite terrible. And that's what I wanted to achieve. And I thought that like 50 is too much. Yeah, 50 is too much. We have reached an unstable point in our system. We do now have oscillations. Right? And this is so extremely important for tuning a controller right now. Right? Do you see this? Imagine being in that car right now. Is there flow coming out? Yeah, I have a little bit of outflow. They're up there. Like a little bit of discharge I have, yeah. Yeah, we have oscillations going on. Right? This is oscillations. Oh no, that's bad. Let's look. So, ooh, this looks spicy. Look at this. Oh no. I'm like the funny uncle version of the PLC class. Oh, I mean, I'll take it as a compliment. Right? This is actually a fantastic example. Yeah, I do absolutely love this example. Right? You see this? This is right now. My controller. It's not. I mean, it is resonance. Yeah. It is a little bit of resonance going on there. Yeah. Let's have the scaling in there. It kind of looks okay here, right? But what we start having is we do start having oscillations. How do I zoom in on just the Y layer? I can't. So it doesn't matter. So we have a little bit of an overshoot here in the beginning. How do I get there? I don't know. A plus. There's a plus icon. I'm an old man. I have to press the plus button now. So here, right, the brown one. So we go a little bit above, and then our controller tries to react on this very, very aggressively. Right? If we're above, it turns off, of course. As soon as we get below, because the proportional part reacts very strongly, we will react very strongly. Not at 100%, it's not a full on-off controller yet, but it almost is. So if the P part would be infinitely strong, we have an on-off controller again. Yeah, this is an on-off controller. Now what we could do, Emil, yes, 100%. We could take this right now and tune it. Right? This is now what we need to do for tuning is, and I will wrap up the stream with this probably. Right now we do have those oscillations, and they're way too strong. Probably they started at like 30 or so. What you do in controls is, if you have a system and if you want to have the perfect the perfect values here, right? You would slowly raise this. So at 5.0, we saw we cannot get to the set point. Then I would slowly raise it. I would say 7.5. We're getting closer to the set point. And then 8.0, we're getting even closer. Maybe 9.0, we're getting even closer. And then at 10.0, for example, we start having an overshoot. And we start having those oscillations. Right? At some point, this behavior that we have will start, which in my assumption is around 20 in our case. Now, and what I would do with this is I would not like I would tune my controller, which there are standard methods. Like tuning the controller would now take and I will leave this then. Oh, this is fun. Like tuning the controller right now to find the perfect P, right? I would look at the difference between our oscillations here. What's the time difference? And I can see the time difference is 0.83. I mean, this is almost perfect here. Almost 0. I don't know. Maybe 0.1. Let's say 0.1 seconds. Oh no, 0.1 minutes. Can anyone calculate how many seconds is this? I can't. Wait. 0.1 minutes in seconds. 6 seconds. This is embarrassing. Yeah, this is approximately 6 seconds. Right. So approximately 6 seconds from this part. Right. The smaller oscillations here, by the way, those are now errors in the sensor. So the smaller oscillations don't really matter right now in our case, because this is completely the simulation, and because I exaggerated with the values. So we would have 6 seconds. Now with those 6 seconds, we could put this into a tuning table, right? I do have one. Oh, by chance, I do have a tuning table. Oh God. We would now, let's assume this would start happening at 25, at a P of 25. Or the P factor of a proportional gain of 25. Let's assume this would happen at this. I could test this now, I will not. What I would do then is I would take this and take one of the tuning methods. The Ziegler, let's take the ZN tuning. The Ziegler-Nichols method. Oh, this is right now, I feel so nerdy right now. This is incredible. Do I have this in English? No, I don't want to donate anything right now. Thank you very much. No, this is not available in English. Are you kidding me? Oh, it's in English. Sorry. You will start until... I love this for me. With a pure P controller right now. Right? I would be able to... Oh God, I don't know how to read it anymore. It's been so long. The oscillation period is TU, the ultimate there. How do I get to the proportionate, to the pure P? How do I get KU? How do I get to KU? KU, the ultimate gain, is defined as 1 per amp. M is the amplitude. Oh no, I'm already at the TI. Sorry, we don't need the amplitude. We don't need the. It is in English. I'm sorry. Sometimes I can't read. I'm already at the integrational part. We don't need the. No, we do not need the time yet. The time we would need for the integrational part, which is an interesting thing. What we just need is, by the tuning method, let's assume the oscillation started at 25. What we would just do, 25 is the ultimate gain. The ultimate gain is like, when do the oscillations start? And we would just set the P value to have a nice steady system. If we have a pure P controller at 0.5, that value. Yeah, I'm sorry. I already was in my head. I'm rushing a little bit. So if we start oscillating at, let's assume 25, let's just test it out. Let's say 25 is my assumption is we start having oscillations at 25. That is my assumption. So let's see if we will have oscillations. I know, I know, I know that I could just use AI. I was thinking about it for a second. I could just send the trace to ChatGPT and let it tune it. Yeah, yeah, could do that, but no. But I could have done that. I know. No, we will not do so. So my assumption is we will have oscillations now. Yeah, we have a little bit of an overshoot. Ah, no, we will not. Nah. Let's say 45, 40. And this is what you literally would do in controls engineering, right? You would slowly raise this to a higher level. So now 30. And I would check at 30, do oscillations occur? Then I would go, no, not yet. At 35, do oscillations occur? No, not yet. At 40, do oscillations occur? Yes, they do. Maybe at 50? At 50, we tested it. At 50, they do. But 50 is already too high. You know why you know how I know? Because this reaches 0 again. As soon as this reaches 0 again, you know that the value is too high. Just a little bit here, but it reaches 0 again. So right now 40. My assumption would be maybe 40 could be ish. Now what I would do, what would be done in controls engineering then generally is I would look at the Ziegler-Nichols method. I see, 40 is too high. What should it be now? 40 is when the oscillations start. Oh, I should just have my proportional factor at half of it. So a good proportional gain right now would be 20. With 20, we will not 20.0. We will not get to our set point, but we will almost get there. We will have a decent system. Controls engineering. And here's the catch. Controls engineering can never be 100% accurate. And what we try to achieve is we try to get as close as possible. Right? We can get as close as possible, and all of controls engineering will also always tell you it's a heuristic method. Right? A heuristic method basically means we got to it by trial and error. That's control engineering. All control engineering projects, all systems have used trial and error to get to the values they are. Right? There is no system in the world that is 100% balanced. It's not fully optimized, perfected, or rational. It can never ever be. We will get close to it. All of those values that you have here in this list, they came up, Ziegler and Nichols, those are two engineers, right? Two scientists from the past. They came up with those values by testing. And engineers, system designers to this day use those values to optimize their systems. How crazy is this? It's still random. Not random, but it's not perfect. Can never be. This is good. I'm having fun. This is great. Yeah, let me see. Probably you tried modeling complete systems before. Of course, you can optimize. There is always optimization possible, but there is never 100%. Right? You can go like on a molecular level at some point, and it will never be 100%. Like there is, what is it like on the smallest levels? We can, as far as our model of science goes, to this day, 100% accuracy, no way. And those values are pretty solid, but they will not have 100% system. Systems, control systems are measured in stability, right? In speed and stability. So you try to get a stable system, right? And a fast system. And those values have been proven to be stable and fast enough. No, with our tech nowadays, we cannot do 100%. Maybe never ever. Who knows? And it's fine. It's as like this is close enough. On Bodhi plots, yeah, of course, yeah, you're right. We could, I mean, we could also, yeah, Bodhi plots. Ooh, no, Bodhi plots are not allowed. No, we are right now controls automation, and not even engineers. We are automation technicians right now. We don't care about like details. In this case, like even the simulation, even the communication speed between system and thing here, there's many factors. And you see, it kind of stabilized. It's not 100% stable, but it is very close. But we have this solid state error here still, unfortunately. Now, what would we do to counteract this solid state error? Now, how could we still like this little bit of trash right there? How can we? And this is, of course, where we would improve our system, right? Because a pure P controller will never be perfect. It will get close to it. This is pretty good. Except for in the end there. I think with a P factor of 20, it's pretty good. But a pure P will never be perfect. Let's say this was at 40 and then maybe, yeah, that's fine. Pure P will never be perfect. So what would we do instead? Of course, also implement. I mean, this was nice. Oh no, this is not overwritten everything. I'm going to change my trace here a little bit, by the way. Turn this off. No. There we go. Yeah, can never be perfect. So what we would do, of course, instead is sum up this error over time. Right? We want to have some addition, some integral. Oh, yeah, now calculus. Oh, yes. We want to look at the integral of the error over time, right? We want to see what was the error over time. Like, how can we get closer? And we would use, of course, the integral there. The bigger the integral, the stronger we react. The smaller the integral, the less we will react, of course. Of course, I say. with like, it's not even, I think it is called already advanced calculus, but still, yeah. And now the last thing that I want to do, and now I'm already over. So I will probably take this to the next time because like next Tuesday, maybe I'll add on this. Maybe I'll make a video out of this, though. Could be both. But now what we would do is improve our controller and make it not just a P controller, but a PI controller. Right? And the integrational part would help us with this steady error. That's what we want to counteract. So I could like very quickly add this, but no. Not gonna happen. I'm already over the time here. What I will do though is I will start recording. No, I will stop recording now. I'm going to reset my tank, right? I will now leave this view. I'm going to now download my trace. I'm going to now activate the trace. Why is something happening? There shouldn't be anything happening. Why is anything? Oh, the fill level. The level is still doing things. Okay. And now I'm going to do it's simple calculus. I will, yeah. I mean, depends on. I would say in school it would already be called advanced calculus. I don't know. In Germany we don't have simple and advanced calculus. We just have arithmetic. I don't know. You got 2 hours over your stream like in the past. Oh no, I usually don't. Yeah. So let's look at this, right? Yeah, yes, this is right now good. This is what we want to see. This is exactly what we want to see. This P controller, it's a pure P controller, has been tuned nicely now. It reacts very fast, 100% speed here in the beginning. Right? It reacts very fast in the beginning. Then it will let go very fast as well. It will not overshoot. Overshooting would be 0 here, right? If we go below 0, that would be an overshoot. It will not overshoot, and it will have a small steady state error, but that is only a small one, right? That is a system, a pure P system, well tuned. And look at this, we just made it ourselves. We have written it. Pete, who used to be my controls teacher, he would be so proud of me right now. And I am proud of all of you for listening to me like for 2 hours now. All of this, of course, like usually you would do all of this in a way smaller amount of time. But I have, of course, I had fun explaining this. I had fun exploring this. You had a lot of questions, a lot of input there, and a lot of help. You helped me a lot there as well. This was great. Right? So I hope. Cheers for Pete, yes. Yes, I do hope you had fun. I had fun. This is great. I hope you learned, maybe you learned something. Maybe you repeated some of the topics there that you already knew about. Yeah, this was way less than I hoped for what I would be doing today. So I hoped for like finishing the PID controller, because right now we could also add, right? We could, I want to add the integrational part, right? The integrational part would be mathematically easy to implement. Easy. A little bit of calculus would be there. But we can, of course, use a pre-made block. There is a pre-made block that does math for us. And this pre-made block is basically why the video is also called PID. There is a technology block here called PID controls. Right? This PID controls block does what we did and way more. So we only did the P part right now. This one does this and way more automatically, right? Like automatically, you need to have a lot of settings, but it helps you with setting this up. Right? Just the integration, Oliver. I will not. No, we will not do integration. No, the integrational part. The problem that I have with the integrational part is we have to enter the second dimension. Right now, all of our system. Hey Artux, hey Michael, or Michael even. Sorry, yeah, I'm wrapping up right now. But you see, wait. Let me leave you with this image. We created our own controller that does this, right? PID controls. Very good. Can I zoom in a little bit? Now this is our PID controller. This is our result. Now the PID block would do this and much more. Like we would just add it to the program. We would need to do a lot of settings. That's what I want to do. And this is what's probably still open. So I hopefully will do this maybe next time. We will see. But this is then a technology object. Right? Maybe you've seen on the left side in your tree there, you have so-called technology objects there. Right? And we could add a new object, and this object would be a PID compact. And a PID compact object leaves us to so much more cool stuff here. Right? I mean, I could probably easily implement this now, but I will not. No. It has to, look at this. Process value limits and process value scaling. This is what we've done mathematically. We did this. Now, one thing I still want to test, because I need to do this, because one of you had a comment earlier on. And I kind of want to have the PID control thing here now. Because one comment that worried me a little bit earlier on. Because one of you said, hey, you cannot simulate the PID compact. And I was like, no, you should be able to. If I can download it, it should be able to simulate it. Yeah, I can simulate it. Technology objects, yay. I would love to finish this now. And you see, we do have the set point. The input would be our tank. And the output PER, I think, would be our output now that we need. And then we have everything that we did. Now we could, and much more. So I will leave this probably next time. This was fun, right? This was fun. But no, I'm not going to go. Like, it's already half an hour too much. Oh, you had to go to the. Oh, it was you earlier on. Okay. But you see, mine is operational right now. That should be fine. The only worry that I have is that I will be running out of license of PLC Sim Advanced next week, so I will still be testing one more thing. PLC Sim, not advanced, standard. That's the one thing that I will test now. So this is now simulating here. And I do hope, I think this might be a problem that we can only simulate it with PLC Sim Advanced. That might be the problem for 1200, because 1200s don't have PLC Sim Advanced. Let me see if this, no, this works. Seems to be working. Hey, Mika. Seems to be fine. So I will, maybe this will be next year, Tuesday. I will think about it. We have many topics. You have given me so much more input that we can talk about, and I will keep up, of course, the TI Tuesdays. I'm having fun. Let's get some rest. This was a lot of math. Maybe I'll have to go back. I will test it. Logical controls there. I will see. But yeah, this was fun. We do have a cool result. Like, really, I think we do have a pretty good result here. Looking at the trace once more, at our measurement here. This was cool. This is pretty good. And I learned some minor things. I didn't think it would work. I gotta be honest. I thought I would mess up the math there or something. But this is great. This worked. Perfect. Good. Then, hey, you just subbed to me. Thank you very much. This is good. Mika, you didn't really. I mean, you missed me live, but the recording will be on. I think I will continue on with this like the next time. This is really great. I had like a lot of fun. But all good things have to come to an end. This graph, our tank system here, absolutely love it. This is great. Right now, I closed PLC Sim, so we can't see it running. But thank you for being here with me. Thank you for like letting me ramble for 2.5 hours now. It's too long. I will have to also get some rest. Thank you. That's cool. You should just do a Hegamon reaction video. You just do so. Send me the link, let me know, and I'll watch it. And then I'll react to the react video. Okay, perfect. Why would you join a class voluntarily of someone just rambling? This is good. Alrighty. Thank you. Thanks a bunch for joining me. This. I love this. Pete would be proud, right? So thank you very much. I will see you next time around. I'm streaming every Tuesday, right? TIA Tuesdays, same time. There's always interesting topics, right? This really I enjoyed. I was already in preparation. I was like, this is cool. This is a cool topic. I love it. Yeah, every Tuesday. Over on Twitch, I stream Wednesdays and Sundays in German gaming. If you want to join there, but no, I'll just be there if you have questions as well. Alrighty. Thanks for joining. Have a great evening and take care. And I'll see you next time around. Wait, I don't have a stop button yet on this. Have to add a stop button.